Okay, now we're ready for section 4.3, distinguishing among atoms. So the first key question here is what makes one element different from another? And there are two numbers that we're concerned about. They're called the atomic number and the mass number. So the first thing we'll talk about is atomic number, and that elements are different because they contain different numbers of protons. Protons are what identifies an element. So the atomic number is the number of protons in the nucleus, and it is identified an element by the number of protons. So that is what we call the atomic number. When we look at the periodic table, we see each square on the periodic table having the symbol or name of the element and two numbers. The number that is a whole number on the periodic table is the atomic number. The periodic table is arranged in order of atomic number, and the atomic number tells us the number of protons. So here's a summary of the first 10 elements on the periodic table, and you can see that the atomic number is equal to the number of protons for every element here on the periodic table. The other thing that we notice is when we skip over here to the last column, the number of electrons, that it is also the number of electrons. The reason that the number of electrons equals the number of protons is that atoms are electrically neutral. That means overall they have neutral charge, and so the number of negative electrons must equal the number of positive protons. Now the next number we're going to talk about is called the mass number. The mass number is the total number of protons and neutrons added together. So positive protons added to neutral neutrons equals the mass number. So in order to figure out the number of neutrons, you can take the mass number, subtract the atomic number, and that will tell you the number of neutrons in an element. There are two different ways to write or notate the mass number along with the symbol for an element. This is called the nuclear symbol notation. So you write the symbol for the element, and on top you put a mass number as the superscript, and on the bottom you put the atomic number. Note it's both written on the left side of the symbol. Another way to write and indicate the mass number is through what's called the hyphen notation. So typically it's written as the name of the element with a dash or a hyphen and just the mass number. So while this was the nuclear symbol notation, this is considered to be the hyphen notation, both indicating the same element with the same mass number. The next key question we're going to talk about are isotopes, and how do isotopes of an element differ? So how are they different? This diagram depicts three different kinds of neon atoms. They are all neon, but notice they are slightly different. The first one is known as neon 20, and notice it has 10 protons because 10 is the atomic number of neon. The next one is neon 21, still having 10 protons, and neon 22, also having 10 protons. If you look and see that all have 10 electrons, 10 positive protons, 10 negative electrons being electrically neutral. The difference comes in the nucleus in the number of neutrons. Neon 20 has 10 neutrons, 10 plus 10, making a mass number of 20. Neon 21 has 11 neutrons, 10 plus 11, making 21. And neon 22 has 12 neutrons, 10 plus 12 makes 22. So the difference comes in the number of neutrons. So summarizing, same number of protons, same number of electrons, so they can be electrically neutral, but they all have different numbers of neutrons. These then are called isotopes. Isotopes are atoms with the same number of protons, but different numbers of neutrons. So neon 20 neon 21, and neon 22 are 3 isotopes of neon. Having different numbers of neutrons causes isotopes to have different mass numbers. So that's really the main key difference. They have different mass numbers. One thing to remember is they are chemically alike, which means they react in the same way because they have the same number of protons and electrons. Those are the particles that are responsible for the chemical behavior, or how something would react in a chemical way. Isotopes have a difference in the way atoms behave in terms of being radioactive or not. So now let's talk about the actual mass of an element. So we know that atoms are very small, so if we're going to measure their actual mass in grams, even the largest atoms are very small. In the 1920s, a device called a mass spectrometer actually enables scientists to determine the actual mass of an atom, and using a mass spectrometer, the mass of a fluorine atom was determined to be 3.1 times 10 to the negative 23 grams. That's really small. So in general, it is inconvenient to work with that small of a number. So instead, the scientists decided it would be more useful to come up with a new unit to measure the mass of atoms. And they used an isotope of carbon-12 as the reference to come up with how big should this unit be. So they arbitrarily chose carbon-12, and if I look at carbon-12, it has 6 protons and 6 neutrons in the nucleus. That's where it has a mass number of 12. So they decided that they're going to take this new unit to measure the mass and say it is that one unit is 1/12 of the mass of one of these 12 items. So therefore, a proton or neutron has approximately 1. Now they came up with a very creative name to name this new unit to measure the mass of atoms, so it is called an atomic mass unit, or abbreviated AMU. So very creative, came up with their best name, atomic mass unit. Because protons and neutrons have most of the mass in an atom, the 6 protons and 6 neutrons account for almost all the mass in carbon-12. And so the mass of a single proton or a single neutron is 1 AMU. Now, one important thing to note when we're talking about isotopes is that most elements occur as a mixture of 2 or more different isotopes. And each isotope of an element has a certain mass and also a natural percent abundance. That's how frequently those isotopes appear in nature. Some elements have isotopes that occur almost entirely as one particular isotope, and there's a small amount of other elements. So looking at hydrogen and helium, we see that one element or one particular isotope has a 99.9% abundance, and then the other isotopes are very small or negligible amounts. So that's true for many isotopes. However, some here in chlorine, you see, has 2 isotopes that occur in slightly different percentages. The 2 main isotopes of chlorine is chlorine-35 and chlorine-37. Chlorine-35, mass number having 17 protons and 18 neutrons, and chlorine-37 having 17 protons and 20 neutrons. Now, if I were to take a straight average of the 2 masses, I would take that I have a mass of 35, which is actually 34.968 AMUs is the mass, the actual mass of chlorine-35, and 36.966 AMUs is the actual mass of chlorine-37, and I add those 2 up and then divide by 2, which is how we take a direct average or mean. We get an average atomic mass of 35.986. However, if I look at the periodic table, I see that the actual atomic mass is 35.453 AMUs. Why is it different from the average of the 2 numbers? Well, what we need to take into account is that these 2 isotopes do not occur in nature in the same percentage. Chlorine-35 is about 75% of the naturally occurring chlorine, whereas chlorine-37 only accounts for about 24%. So if I were to pick up a random chlorine atom, About 75% of the atoms are chlorine-35, and only 24% of them are average of chlorine-37. So if I were to scoop up a whole handful of chlorine atoms, I would not have equal numbers of the two different isotopes. So the average mass is not just a straight average. So the atomic mass, sometimes called the average atomic mass, is what we term the weighted average of the atoms in an element. Now, weighted average means we take into account not only the mass of the isotope, but also the relative abundance as they occur in nature. So here's what we do. We take the mass of each isotope multiplied by its abundance, and then add each of those together to find the average mass. So we'll take the mass of isotope 1 times the abundance of isotope 1, and then add it to the mass of isotope 2 times the abundance of isotope 2, and then add it to any more isotopes that we have. And that's how you would find the average atomic mass, or the weighted average. So here's an example. Carbon has two stable isotopes, carbon-12, and a natural abundance of 98.89%, and carbon-13, abundance of 1.11%. So we take the 12.00 AMU for the first isotope times its abundance as a decimal, and then we'll take the second isotope, 13.003 AMUs, times its percent abundance as a decimal. So then we do those two calculations, so mass times abundance of the first isotope and mass times abundance of the second isotope, and now we just add them together, and we come up with 12.011 AMUs, and rounding to the correct number of significant figures based on our original measurements, 12.011.